Okay, welcome to the Computational Fabrication Seminar. We have two speakers for today's session on Fabrication OL shape decomposition. Okay, welcome to the Computational Fabrication Seminar. We have two speakers for today's session on Fabrication OL shape decomposition. We will start by introducing our motivational talk speaker, Dr. Marco Livesu. Marco Livesu is a tenured researcher at the Institute for Applied Mathematics and Information Technologies of the National Research Council of Italy. He received his PhD at the University of Cagliari in 2014, after which he was postdoc researcher at the University of British Columbia, University of Cagliari, and the Institute of Applied Mathematics and Information Technologies of the National Research Council of Italy. His main research interests are in computer graphics and geometry processing for manufacturing and engineering applications. He is a creator and lead developer of CNR-IMATI, a C++ library for processing surface and volume meshes. Dr. Marco Livesu's talk will be on fabrication OL decomposition. So the floor is yours, Michael.
Thank you, Pam. So let me share the screen. Can you see the screen?
Yes.
Okay. So first of all, I would like to thank the organizers of this wonderful seminar. I'm really excited about being here and giving this presentation. So thank you for inviting me. And so in this motivational talk, we will try to kind of survey the shape decomposition approaches that are used in the context of digital fabrication. Okay. So in this context, typically shape decomposition is intended as a mean to overcome the limits of the fabrication hardware, such that if you have something that is not directly fabricable with a machine that you have at your disposal, you can work it through decomposition in order to decompose it into simpler pieces that actually fit in your machine in terms of size, geometry, and in general properties that are restricted by the hardware that you have at your disposal. There is a bunch of different applications that relate manufacturing and shape decomposition. Probably the simplest one is decomposition because of size constraints. Let's say that you have a 3D printer which has a printing chamber of the size that you see in the image. And this is not big enough for you, for example, to 3D print a chair. So if you want to do that, the only way that you, well, actually you have two options. Either you spend more money and you buy a bigger 3D printer, or you split your model into simpler pieces, which are smaller, and therefore they can fit your hardware. And so you can then reassemble everything together to make the final object, as in this case. So that's one typical example of shape decomposition for manufacturing. Other methods are mainly related with the ability to control the geometric properties of the objects. And this is mostly about controlling the angle between the local surface orientation, so the surface normal that here is intended with the vector end, and the machining direction. And this machining direction in the slide can be, for example, the direction of which material is extruded when you have a 3D printer, or for example, can be the orientation of the drill bit in a CNC milling machine, so the direction of which you actually carve away material from your block. And one important property that you may want to strive for is to control this angle and make sure that this is always convex. And when this is the case, you get a piece of geometry which is called a height field, which is a very important property for manufacturing, because, for example, in 3D printing, whenever you have an height field, you can go for printing without supporting structures, for example. And if you have, for example, a CNC milling machine with 3 axes, you know that in a single machining pass, you can produce the whole object because essentially the drill bit can reach any point on your surface. So this is a pretty interesting geometric property for fabrication. On the other hand, whenever you have an angle which is more than 90 degrees, you have what is called an overhang. And for the case of 3D printing, for example, you will need to insert some support structures here to sustain this part of your object from below as you proceed with the fabrication. And if you have a CNC milling machine with 3 axes, this is actually something you cannot fabricate unless you change the position of the drill bit or of your object, or you work it through decomposition, and so you decompose this object into simpler pieces that at this point will be of this kind, and so you know you can fabricate them. So that's another typical application for shape decomposition in this context. Other things regard, for example, the ability to create objects that are composite. For example, they are multi-material or multicolor, and maybe you have a printer that is not very sophisticated, so you have just one filament of a single color and material at your disposal, and so this is not something that you can fabricate as it is. And you can, for example, apply decomposition in order to split your object into simpler pieces, which are homogeneous in their color or material. And therefore, by, for example, changing the filament, in this case, to adapt the color to what you want, you can fabricate every single piece alone, and then you just reassemble together the things to get a multicolored object. Other decomposition approaches strive for a better surface finish. In 3D printing, for example, 3D printing is also called layered manufacturing because essentially you deposit material one layer on top of the other, and this generates a typical staircase effect on the profiles of the things that you fabricate. And so what we know is that if you take a certain building direction, any point on the surface where you are nearly vertical, you have a very good approximation of your intended shape, which is this curved line. But when you are nearly horizontal, the error that you commit in the approximation of your object is pretty bad. And so if you print your object as a whole, there's nothing you can do. You will have lots of them in any case, but you can improve the surface finish of your objects, for example, splitting them in multiple pieces, such that you try to promote a lot of these nearly vertical configurations and discourage nearly horizontal. So that's another way of applying the composition for manufacturing. Always for 3D printing, as I said before, whenever you have an overhang, you need to put supporting structures. And that's an issue for many reasons. So, for example, because you waste material, but also because once you're done with the print, at some point you need to remove all these supports, and this can create lots of artifacts on the surface because you're essentially breaking the material, and so the surface will not be very polished. In this way, shape decomposition can be helpful to you because you can split your object into simpler pieces in order to reduce the necessity for supports in the first place, and also to be a little bit smarter and try to position them in the parts of your object which are not very visible. For example, if you're printing something for which you know what are the major features of the object, you may want to do a decomposition and an orientation of the object during fabrication that avoids the insertion of supporting structures in the most visible parts of your object. And this, for example, something that was done in this project that was published 2 years ago. Another important application is collision avoidance. In this case, we have a complex setup where essentially you are printing something which is attached to a robotic arm with 6 degrees of freedom. And differently from the typical scenario of 3D printers where you have like flat layers and therefore the possibility for collision is 0, you have by construction no collisions. In this case, you need to explicitly make sure that whenever you move your robotic arm, you do not collide, you do not create collisions between what you have already built and the extruder, which is steady in this environment. And this has to be done explicitly because it's not something that is intrinsic in the way you are fabricating your object. And essentially here, you are applying a shape decomposition algorithm that works at the level of the slices. You are essentially defining a bunch of curved slices that will allow you to avoid collisions. Another important application, and this is the last one that I'm going to mention, is packing. In this case, essentially, you want to ship something, and in order to reduce the cost of shipment, what you want to do is to find the tightest box that contains your pieces. And so you're looking for a dense packing of your object on the one end, and on the other end, you don't want to create too little pieces because otherwise reassembling them will be complex. And so you're looking for kind of an optimal trade-off between the number and size of your pieces and a tight packing of them in order to be able to ship in a small box. And there are many other applications that I'm not mentioning. What I would like to stress is that shape decomposition in manufacturing comes in very different flavors. And there is lots of stuff, lots of algorithms and approaches going on. So in the second part of the presentation, essentially, I will try to kind of summarize what are the major approaches to solve these kind of problems. Before we go there, just a little comment on how complex it is to decompose something. Let's say that if you want to compute a general decomposition, this is pretty easy. You take a mesh and you take, let's say, a cutting plane that halves your object, and that's it. If you don't have specific requirements, this operation is super easy. If you want to compute something that is a constrained decomposition, so if you have some requirement on the size or the geometry of the part that you are going to create, this is a little bit more complex, but still relatively easy. And the reason why it's easy is because you can play with 2 degrees of freedom that are unbounded, and are the number of pieces that you're going to create and the size of the pieces. And in particular, if you don't care about the number and the size of the pieces, you can always detach tiny little pieces from your object, and therefore computing a constrained decomposition doesn't become too much complex. What makes the complex real hard is when you want to compute a constrained decomposition that is minimal in the number of pieces. And this is something that is known to be NP hard already in 2 dimensions. For example, convex decomposition of polygons is already NP hard, and so it is in 3D. And the problem here is that the search space grows exponentially, and we have no hope to find the global minimum, also because the size of the problems that we deal with in practical applications like manufacturing is so big that trying to explore the whole space of solutions is just infeasible. So in this scenario, essentially what we do is to strive for a good local minimum, whatever good means. And this depends on the application typically. And it's all about picking the right heuristic. So having the right idea is of paramount importance. Okay, so despite the many different applications and many different manufacturing technologies that we have, like laser cutting, CNC milling, 3D printing, molding, and so on and so forth, all these shape decomposition methods more or less try to control the same aspects, which are these 2, the size of your parts, and this can be thought of both in the static version or in the motion version, especially when you want to solve assemblability problems. You have the trajectory of your object, and you want to control the size of your object through a trajectory in order to make sure, for example, that things can be reassembled together. And the other important property that you want to control is the local surface orientation. And as I said before, in particular, you want to control the angle between the surface orientation and the machining hardware. For example, the angle of the position of the material or the angle of the drill bit in CNC milling. The way algorithms try to achieve this goal to control these aspects is mainly through 3 approaches that I mentioned here. One is binary space partitions, for example, cutting planes that are applied recursively to your object. One is graph labeling, where typically you try to solve some sort of graph algorithm like min cut max flow, for the case of bipartition of the graphs, or some extensions of this idea, for example, graph cuts, which does the same thing, but considering multiple clusters of nodes. And there is also a number of approaches that exploit mesh booleans. And these things can also be combined together for more complex algorithms, but more or less the ideas that you find in the literature are these 3. So in this presentation, for the sake of time, I'm going to focus mostly about how binary space partitions algorithms work. And if you are interested in seeing the full story, I invite you to join a tutorial that Peng, Ziki, and I will give at Eurographics 2022, where essentially I will do like an extended presentation on these topics, and I'm going to talk about also graph labeling and mesh booleans. Okay, so let's say something about binary space partitions. There is a variety of different algorithms in the literature, like many. These are just 4 of them. And in terms of applications, they aim to control, for example, the size of the objects, the surface finish to reduce the staircase effect, packing for shipping. There is pretty much applications in any of the fields that I mentioned in the first part of the presentation. If we take a look at the methodology that they use, we have mainly 2 methodologies. We have algorithms that proceed top-down, using beam search to increase the number of solutions that they explore in order to find a better local minimum. I would say something about how these techniques work. And then there are methods that work in the opposite way. So they work bottom-up, typically with a greedy strategy. So let's see bottom-up versus top-down. First, if you go bottom up, typically your input is kind of a mesh representation of your object, let's say a triangle mesh or a volumetric mesh. And what you do is to create a tree in which the leaves of your tree are the single elements of your mesh. In this case, all the triangles that compose your mesh. And then you construct this tree proceeding upwards by combining elements in your mesh that are adjacent in the connectivity. And so in the beginning, you merge two triangles to form quads, and then you proceed until essentially you hit the root of this tree, which represents the whole mesh. And once you have this representation of your geometry, essentially the inner nodes in your tree representation constitute cluster of elements that define your decomposition. And so if you merge things according to some manufacturing-oriented criterion, what you have is a decomposition that kind of fulfills these requirements. And the most important thing, therefore, is how do you merge things? What is your merging policy? This is what really differentiates the different algorithms. And one important example in this category is, for example, shapes in a box, which aims to find a good packing for a given object. And in this case, this algorithm in particular works with a volumetric representation. So the nodes, the leaves of the tree will be tetrahedra. And the merging policy aims to minimize an energy that is called absolute aboxiness. What is? It's essentially the difference in volume between the tightest oriented bounding box that is containing your current cluster minus the volume of the cluster itself. Of course, the smaller this volumetric difference, the tightest is the fitting of the box into the cluster. And so just by minimizing this energy, all the merging happens. The alternative strategy to bottom-up is top-down. And in this case, you start from the root of your representation, which is, again, your input geometry, and you proceed by cutting. Cutting can be done, the simplest version is through cutting planes, but you can also consider something more refined, for example, implicit functions defined through RBFs or stuff like that. So anytime you cut, you split your object in two, and so you go down in the tree, and you continue until you're happy with the geometry that is contained in the leaves of your tree. And as for the example before, the most important thing is how do you cut? What is your cutting policy? And a good representative of algorithms that operate in this fashion is probably Chopper, which was, I guess, the first one that was proposed in this fashion. And in this case, what they do is to consider a discrete set of candidate planar cuts. Let's say they sample the Gauss sphere, and every single sample will give you a candidate cutting plane. And so they evaluate the ability of these cutting planes to minimize a metric that is based on the number of parts that you create, the possibility to put connectors in an easy way, fragility that may arise because maybe you make parts that are too thin, and so maybe they may break, and other things. So summing all the scores for all these metrics, you get a winner. You get a cutting plane, which is the best one according to this criterion, and so that's the one that you use to define the subcomponents in your decomposition. So this is how can you build your trees. Regardless of whether you go bottom up or top down, you may have different ways of exploring the space of solutions. The simplest possible way is what is called greedy. Greedy means essentially that at every single point in your algorithm, you take the locally optimal choice. For example, if you have a bunch of cutting planes, you just take the best cutting plane according to your energy. An alternative, one of the problems of greedy is that depending on how you define your energies and your algorithm, you may get stuck at local minima, which are not very useful for your application. And so people try to kind of explore more solutions. And one way to do that is to use what is called a beam search. Beam search is a method that allows you, as I said, to explore a wider portion of the feasible space. And it's based on the assumption that you can rank your partial solutions. And if you can do that, at every point in your algorithm, you can essentially take, okay, these are my solutions. I'm going to sort them from the best to the worst, and I'm going to propagate my splitting decisions only considering the n best possible solutions, where this n is a parameter of the algorithm and it's called the beam width. So it decides how many interesting directions you want to continue exploring, essentially. And this essentially defines a graph like this, which encodes the space of solutions that you are exploring. So every single node in this graph is a decomposition. So is a tree that represents, for example, a binary space partition. And every single node in the arc, and in particular, the number of outgoing arcs from every single node represent the alternative local moves that you have. For example, in the case of Chopper, where you consider a bunch of cutting planes, you will have one of these arcs for every single cutting plane. And so you're going to sort all these things according to the energy that they have, and you're going to propagate only the n best solutions. In this case, n is equal to 2. And so in the next step, again, you're going to have as many local solutions, twice the number of local solutions that you had before, because you propagated 2 solutions. You're going to rank all of these and take the best 2, proceed to the next level until you converge. And you converge when essentially in the leaves, you find pieces that fulfill your input requirements. At that point, you will have n candidate solutions, and you take the best one among them, which will be the final solution of your problem. That's how beam search works. Okay, just a few words about labeling without entering so much into the details of how these methods work. Labeling is the other prominent method to decompose objects for manufacturing. And there are mainly 3 categories of approaches. One is labeling through the resolution of optimization problems, for example, integer linear programming, max flow, or X extension to multiple labels, which is GraphCut. There is a lot of literature that is based on these ideas. On the other hand, we have greedy approaches, which just follow the greedy idea. At every single point, you apply the best local decision. And then we have something which is in between. There is a bunch of methods in the literature that kind of proceed in 2 steps. They first over-segment, so they compute a super segmentation of what you provide in output, and then they do a region merging. They take these small clusters and they try to merge them together in order to find the output pieces. And when you apply this technique, typically it's a combination of the previous 2. For example, it's very easy to see the first part, so the over-segmentation part, which is done greedily, and then the region merging, which is done, for example, through the resolution of an ILP. I'm not going to enter into the details, but I just want to make the statement that also for the labeling approach, greedy methods, if you have the right idea, become very powerful. And this is also an occasion to link my presentation to the next presentation that Thomas will give. So these are 3 works that were co-authored by pretty much the same authors in recent years and are about molding. So they solve a complex problem. And in particular, the latest 2 versions, so meta molds and volume-aware molds, produce the geometry of these molds by solving labeling problems. Meta molds is based by this idea of computing a surface labeling by solving an integer linear program. And the latest one, volume-aware mold, is a greedy method. So it's based on a very simple idea, which assigns a label to a volumetric representation of your object based on shortest paths from the inner points of the volume to the boundary of your hull containing the object. And what I find interesting about this line of works and these approaches is that this is the time evolution of the works. So they started in 2016 and ended up in 2019 with this flexible mold trilogy, let's say. If you take a look at the results, of course, the latest one is going to be superior to the previous ones because you always have to improve, right? And these are all SIGGRAPH papers, so they did better to improve. Otherwise, we wouldn't be talking about SIGGRAPH papers in the first place. But if you take a look at the complexity of the problem, the complexity of the formulation, it's actually the other way around. So they started very complex in 2016. They had like a more refined and clean, if you want, solution, which was based on an ILP labeling in 2018. And only at the end, in 2019, they had like the most simple approach, which is purely greedy. And to me, this is amazing because it's really simplicity as being complexity resolved. So it's like the proof that it takes a lot of time to have like simple ideas. So in the beginning, they were like kind of solving a complex problem with complex tools. And eventually they were able to have simpler ideas, which were even more powerful than the previous ones. And so I'm really looking forward to the presentation of Thomas, which will be talking about all these things and even more. And this is also an occasion for me to conclude the talk. I would just like to say that remark once again that shape decomposition is a great tool for digital manufacturing. There is like lots of approaches, as I've shown in the presentation. Minimal decompositions, which is what we look for, are extremely complex to compute, and from the theoretical point of view, are NP hard. And so it's all about having the right idea and picking the right heuristic to find solutions that are useful in practice. And the other important thing for me is that greedy is not a bad word. And if you have the right idea, greedy methods will be easier to write, to debug, and probably more predictable in terms of the results they produce. So I thank you for the attention, and I leave the stage to Thomas.
Yeah, thank you, Marco, for the inspiring talk. Our second deep dive talk speaker is Dr. Thomas Alderighi. So Thomas Alderighi is a researcher at the Institute of Information Science and Technologies of the Italian National Research Council, where he is a member of the Visual Computing Lab. He received his PhD from the University of Pisa this past February, supervised by Dr. Pino Signoni and Dr. Luigi Mano. His research focuses on the application of computational geometry to the automation of digital fabrication process, with a particular focus on the automatic design of molds. Dr. Thomas' talk will be on shape decomposition for automatic mold design. So Thomas, the floor is yours.
Okay, can you hear me well?
Yes.
Yeah, so first of all, thank you for the invitation and also for the nice introduction. And also thank you, Marco, for preparing the ground for my presentation with your motivational talk. So my talk today would be about the application of shape decomposition methods to solve problems related to the automation of mold design. And, oh, sorry. Okay, so in my research, I've been working on applying shape decomposition as a common methodological framework that enabled me and also my group to solve different problems related to manufacturing. And I've been doing so with a particular focus on automatic mold design, but we are also applying it to other problems related to manufacturing, like the partitioning of 3D printed objects to reduce the visual impact caused by support structures using FDM prints. And today, in this deep dive talk, I'm going to focus on two of my recent works about the automation of the design of rigid molds based, and this method will be based, as you will see, on a numerical optimization approach. And the second work I'm going to present you today instead is about the automation of the design of composite flexible molds that we presented at SIGGRAPH 2019, that instead, as Marco introduced, relies on a purely geometric approach. So before starting with a deep dive, I want to give you sort of a common ground. So for those of you that don't know what molding is. And molding is a very powerful manufacturing technique that is particularly efficient for the fabrication of objects in mass, so for mass production. And the importance of molding as a fabrication technique has been proved throughout history by its widespread adoption in industrial mass production, for example, for plastic and metal parts. And most probably, most of the plastic objects that you have lying on your desktop today are probably made in some plastic injection molding facility somewhere in the world. And why molding is so efficient? Well, it is so because it has several good properties that make it very convenient when compared to subtractive or additive manufacturing for mass production. And these properties are its low cost and fast part manufacturing, and also the fact that quite often, depending on the mold material, you can handle a wide range of materials within a single mold. And more importantly, another good property about molding in terms of fabrication technique is that it guarantees a very high precision and reliable manufacturing process. However, all these advantages come with a very highly constrained fabrication process, and this makes designing good rigid molds a very complex task. And as you can see from the picture here on the right, an industrial mold will have many moving parts that you need to carefully design and optimize for. And in particular, designing a mold requires you to solve engineering problems like the optimization of the material flow within the mold. The design of the mold tooling requires to operate it, and also gate locations and so on. But in my contribution, and also throughout this talk, we will be focusing on the geometric aspects related to mold design. And these required the optimization of the parting direction assignments, and also the optimization of the geometry of the parting surfaces. And to better understand what I mean by this, I want you to have a look at a very simple example of how a two-piece mold works. So in a two-piece mold, you have two mold pieces, a top mold and a bottom mold piece, that can be assembled together along what is called their parting surface. And once assembled together, they will form an empty cavity that has the shape of the object that you want to produce. This shape, this cavity can then be filled with some liquid material, like resin or metals or whatever casting material you need to use, that after some physical or chemical process will solidify. At this point, the mold is ready to be opened along the parting direction chosen for the mold pieces, and the part can be extracted and released, and the process can be repeated as many times as you need to replicate your object. One of the main constraints from a geometric point of view that needs to be addressed when designing a mold is the presence of undercuts in your mold design. So to get what an undercut is, suppose that you need to fabricate a bunny shape like this one using this mold decomposition. So what happens here is that the bottom mold part, or the bottom mold piece, will be easily retractable along its direction -d, while the top mold piece will get stuck around the object due to the presence of undercuts. And undercuts are these red highlighted areas here in the picture that correspond to parts of the mold volume that are shadowed by some parts of the object along the parting direction prescribed to the mold piece. And from our perspective, designing a valid rigid mold will amount to defining an optimal mold decomposition and parting direction assignments that ensure that no undercut exists in our design. So the first part of this talk will be about the automatic generation of flexible molds. And here I wrote as a subtitle, Bending the Rules, because using a deformable material instead of a rigid one for the mold allows you to relax the undercut constraints. And indeed, silicon molding or deformable molding is a widely used technique that artists and artisans use to be able to cast very intricate shapes for jewelry and sculpture. And however, the problem with flexible molds is that creating these molds is still a very highly manual and complex craft, in which the mold artists need to manually figure out and create all the internal cuts required to open the mold and release the object. So our first approach at automatizing the process of silicon mold design was MetaMolds. That is a work that we presented at SIGGRAPH 2018 that was based on an optimization algorithm based on surface decomposition that for each part of the object surface would assign a parting direction. And the algorithm would then use this decomposition to automatically create a set of MetaMolds that are these red things that you can see here, that are objects that you can 3D print and that embed all the geometric details of your silicon mold pieces. And a MetaMold is used like this. So you 3D print it, and then you can pour some liquid silicon onto it to create your silicon mold pieces that can be then assembled together and used to cast some liquid material like resin or gypsum and replicate your shapes. The problem with this work, however, was that its surface-based analysis was fairly limited in terms of the possible internal cut layouts that it could produce, being limited to only a knowledge of the surface details of the object. The goal instead with the first contribution that I'm going to present in this deep dive talk was to automatically generate two-piece flexible molds for casting very intricate shapes like this one, where you have multiple connected components when the internal one is free to move inside the other. And we want to do so without having to decompose it in multiple simpler parts. And doing so requires the geometric characterization of all the internal cuts layout that are needed to release the object from the mold. But more importantly, it also requires the definition of a robust and efficient algorithm that enables you to actually compute this cast geometry. So we achieve this by defining a volumetric analysis of the mold volume surrounding the object that characterizes the geometry of these cutting surfaces based on a purely geometric approximation of the mold extraction process. And these surfaces are divided in two kinds. So the first are the parting surfaces, that are the blue ones here, that divide the volume into the two separate mold regions or mold pieces. And the second kind of surface are the additional membranes. These are all the casts that are required to ensure the mold extractability from topological and geometrical features of the object. So before going into the actual description of how we implemented this algorithm, I want to give you the the intuition in the continuous setting behind this analysis. So as I told you at the beginning, this is based on a geometric approximation of the trajectories that each volume element of the mold would follow during the extraction process. And we call these trajectories the escape paths. And what is nice about escape paths is that they continuously vary as you move inside the mold volume. However, there are some points in the mold volume where this continuity property doesn't hold. At this point, they admit more than one valid escape path at the same time. And well, it happens that these are exactly the points that characterize the geometry of the cut layout required to open the mold. As in those points, during the extraction process, the mold will stretch along distinct parting directions and eventually end up wrapping around some parts of the object. So it is exactly there that we want to place our cutting surfaces. So this was the idea in the continuous setting. Now let's see how we implement this in the discrete case. So the escape paths in the discrete case are defined as minimal walks or shortest paths that connect interior vertices of our mold tessellation to its external surface. And this here is just a fancy visualization for you to visualize some of the escape paths defined for the mold of this fertility shape. Now let's see how we implement this. So the first step is the definition of the mold volume. And we define the mold volume to be the volume contained between the object surface and the convex hull of an offset surface of distance d from the object. We do this so that we can enforce a minimum thickness of the silicon mold around the object. This volume then is discretized using a tetrahedral tessellation using common tools like TETGEN or TETWIFE. Then this will be the input of our algorithm. And the first step of the algorithm is, since we are working with two-piece molds, is to define the two approximate parting directions. And to do so, the algorithm selects the pair of parting directions that maximize the total accessible surface and partitions the external boundary according to these directions. So given the external boundary partitioning, the escape paths are then computed as geodesic shortest paths that connect the interior vertices of this tessellation to the partitioned external boundaries. And here I'm showing you the 2D parallel of the algorithm for easier visualization. So once you have computed the escape paths, the algorithm needs to check for each pair of adjacent vertices or for each pair of adjacent escape paths whether it needs to be traversed by a cutting surface or not. And there are three possible cases here. The first case is when you have to insert some part of a parting surface between the two vertices. And these are trivially identified as the first escape path computation. Looking at it, you can assign to each vertex of the interior of the mold interior a label depending on the external surface partition in which its escape path ends. So this partition the interior mold volume into two regions, and the parting surfaces will be then defined to cut through all the edges that cross the boundary between these two regions. The second possibility is when you need to insert an additional membrane between two adjacent vertices. And this requires a more complex check. And for each pair of adjacent vertices, what you do, and this is for the 2D case, what you need to check is whether their escape paths, they enclose some parts of the object or not, like it happens for this case. And in 2D, it is sufficient to do this check. And as you can see, the output is a set of additional membranes that are shown in red here. And instead, if the two escape paths are able to freely reach the external boundary, no cut is needed. And it is the third case. So in 3D, we have exactly the same concepts. And first, we compute the geodesic path for interior vertices to the external boundary. Then parting surfaces are treated as in the 2D case. While to check for additional membranes, what we need to check is checking if the minimal surface or approximate minimal surface that is bound by the escape paths for the two adjacent interior vertices intersects or not with some parts of the object. If it does intersect, we need to add a part of the additional membranes. Otherwise, no cut is needed between those two vertices. So the output will be a set of parting surfaces and additional membranes. So once the membranes are computed, the algorithm proceeds to the generation of the metamold and hard shell geometry. So the metamolds will embed all the details and geometric details about the cutting surfaces and additional fabrication details like the air vents, the material inlets, and all the registration details required to keep the mold in place. The hard shells instead are defined for two, they're created for two reasons. The first one is that they allow you to shape the silicon mold external shape. And the second reason is that they allow you to keep the flexible part of the mold, the silicon mold, in place during the casting procedures so that you can have a better accuracy in your replicas. At last, the last step of the metamold design process is to select the best silicon and resin casting directions so that you can minimize the risk of having air bubbles trapped inside your cast. So given the metamold geometry, the fabrication pipeline is then divided in two phases. The first phase is about creating the metamolds and the silicon mold. So first you 3D print the metamolds and shell, and then use them to pour silicon inside and create your silicon mold pieces. While the second phase is the casting phase. And this you can repeat as many times as you need to create many replicas of your object. And in this phase, you assemble the composite mold, then you pour some liquid material into it that can be resin, gypsum, or even low melting point metals, and cast your shape. And finally, you extract the object from the mold and repeat this process over and over. So now I want to show you some of the most interesting results that we obtain with this method. And this one is for sure the most exciting one that features multiple connected components where the internal one is free to move inside the other, and also features a complex knotted geometry. And as you can see, our method was able to robustly characterize all the interior cuts that are required for a successful cast of this shape without having to decompose it. And this is another interesting example in which you see how the snake hairs of the Medusa exhibit complex geometrical and topological features for which our algorithm was able to generate a set of cutting membranes that finally adapt to the object geometry. There are, of course, some limitations, though, that are more or less related to the fabrication technique per se. The first big limitation is that since you are not going to decompose the object into multiple simpler parts, this method is really not able to fabricate objects that have bottle-shaped features or very large hollow cavities, as in this case, parts of the mold will get stuck inside these cavities and won't be extractable. A second major limitation comes from one of the advantages of using silicon, that is its flexibility. And because of this, whenever you have some thin slivers inside your silicon mold design, what happens is that these thin slivers can deform under the effect of gravity during your casting procedures and eventually lead to some inaccurate casts. Another limitation is that flexible molds do not really scale well with high volume productions, as handling a deformable mold is very complex to automatize in an industrial setting. And this is why industrial production mainly relies on rigid molds for mass production. And this brings us to the second contribution that I'm going to present you in this deep dive, that is about the automatic design of rigid molds. And this time, the subtitle is Divided Impera in Mold Design. And this is because when going back to rigid molds, what you need to do is that you need to fully account for the undercut constraint that I introduced you a while ago. And this constraint poses an hard limitation on the solution space that you can explore with your method, and thus limiting the range of shapes that are actually manufacturable using a rigid mold. But in this approach, we exploit a divide and conquer approach to decompose the object volume into a set of parts that individually are guaranteed to satisfy the height field constraints. So that for a pair of opposite parting directions. And this means that each of these parts will be manufacturable using a two-piece rigid mold that is easy to fabricate and also to operate. And then all these parts that can be individually cast are assembled together and glued together into the final shape. So before describing the method, I want to give you a general context about the state of the art in automatic mold design. And here I will plot recent methods for computational mold design, where on the x-axis, we measure the complexity of the manufacturable shapes in terms of geometric complexity. And on the y-axis, we show instead the complexity in terms of handling and also fabrication of the molds required to generate such shapes. And as you can see, there has been this trend in recent years of providing solutions that are able to produce more and more complex shapes, but at the cost also of increasingly complex mold designs. And here in the top right corner, you see methods for the automatic generation of flexible molds, while in the bottom left corner, you see methods that address the automatic design or supervised design of two-piece rigid molds that are very efficient to use and also to fabricate. And with this method, instead, the idea was to invert this trend and follow the road started by Nakashima et al. In 2018 with core cavity, that is a user-driven object decomposition method for two-piece mold generation. And instead, with this method, we provide a fully automatic pipeline for the generation of two-piece molds based on object decomposition. So to achieve this, the algorithm that is designed to address three main goals. The first one is that given an object shape, we want to obtain a volumetric partitioning of it. And the second goal is that since each of these parts will need to be manufactured using a two-piece rigid mold that opens along a pair of opposite parting direction, is to enforce locally to each part the double height field constraints for a pair of opposite parting direction. The third goal, finally, is that since you will be casting all these parts individually and then reassemble them together, is that you need to ensure the global assemblability of all these parts into the final shape. So the main concept to achieve this in our method is the definition of a novel DHF accessibility property, or double height field accessibility property. And this property says that for any point within the object volume and for any candidate direction D, that point is DHF accessible from D if and only if, casting array along that direction, there exists no front face occluder along it. And if this happens, in this case, we color the region in green and we say that it is DHF accessible. Otherwise, we color it in red and that is not accessible. And what is nice about this property is that the green region, or the accessible region, is guaranteed to have no self-occlusion along direction D, as we are directly sampling it, but also implicitly also along direction -D, as self-occlusion must be mutual along a pair of opposite parting directions. And this means that the DHF accessible region is guaranteed to be locally a height field with respect to d and minus d. And also, since we are also checking for global occlusions along that direction, this means that it will be globally assemblable from that direction. And what is important to note here is that the DHF accessibility can be very different for pairs of opposite directions. And this is due to the global accessibility property that we are enforcing at the same time as the height field property. So the algorithm we define works in 3 steps. The first step is the evaluation of the DHF accessibility property for a set of candidate parting directions and for each volumetric element of your shape. Then the second step uses this information to optimize a volume decomposition of the object into parts that are guaranteed to be a double height field. And finally, the third step is the automatic generation of the 3D geometry of the required molds for each of these double height field parts. So let's have a look at the second and third step now. So in the second step, we address the decomposition into parts as a multi-labeling problem in which we optimize an assignment of DHF accessible directions to elements of the object volume. And we carry on this numerical optimization, focusing on these desiderata. The first one is that we want to have a small number of parts so that we can keep the fabrication process and also the assembly process simpler. The second desiderata is that we want to avoid having tiny parts because they're very difficult to fabricate, but also to assemble together. And finally, the third constraint is that we want to define smooth seams and also to locate these seams on less visible areas of the external surface so that they will be less visible on the final assembly. And we achieve this casting this problem within the GraphCut optimization framework that is a very efficient method for computing multi-label assignment problems that can be expressed as an energy and functional minimization problem where the energy functional has this shape. So you have 3 terms, a data cost, a smoothness term, and a labeling cost. And this is efficient, but however, it has some limitations though, when compared, for example, to general ILP formulations or integer linear programming formulations. And that is that the fact that you cannot explicitly model general constraints within this optimization framework. Instead, you have to embed these constraints in your energy function. And in fact, the data cost in our algorithm will represent the cost of assigning a given direction to any element in the object volume. And we use this data cost to model the hard constraints that are given by the DHF accessibility property. And we do so by assigning an infinite cost to parts of the object volume that are not reachable or not DHF accessible for direction D, and instead assign a scalar cost that takes high value close to the non-accessible region and rapidly goes to 0 within the accessible region for any direction D. The second term is the smoothness term, and this penalizes solutions over the length of their boundary and also the visibility on their boundary on the external surface and over the total area of the internal cuts introduced by the decomposition. And we achieve this by decomposing this cost into these 2 subterms as surf that weights in the length of the edges of the boundary on the external surface of the object, weighted by a measure of how visible are those boundaries that is function of the ambient occlusion defined on the external object surface. And the second subterm is as follows, instead weights in the area of the internal interface between 2 adjacent parts of the decomposition. Finally, the last term is a labeling term that penalizes solutions over the number of labels that are required for the object decomposition, and thus implicitly prioritizes solutions with a smaller number of parts. So the output of this energy minimization will be an assignment over the volume tetrahedral elements that partition the object into double height field parts. The next step is computing automatically the 3D geometry of the 2-piece rigid molds required to cast individually all of these parts. And so, as I told you, at this point, we have a set of parts that are guaranteed to be double-height fields. So the first step is to decompose each of these parts into the two height fields for the two directions d and minus d. And we do so this by solving again a labeling problem, but this time we can consider it as a subproblem where only d and minus d labels are possible. And also we do so focusing on a smoothing factor that minimize the boundary length of this decomposition to keep the parting line of our rigid modes as simple and smooth as possible. From this parting line, we then automatically generate the parting surfaces of the two-piece molds using Poisson disk reconstruction, as we have introduced in our previous paper, MetaMolds from SIGGRAPH 2018. And these parting surfaces will then be used to automatically generate the full geometry of the mold that will also embed some fabrication details like the automatic location of air pipes that are needed for the material insertion and also to let the air escape, and also all the registration details that are required for a successful cast. So this concludes the algorithm description, and now I want to present you some of the most interesting results that we used to validate it. And so we validated the algorithm on a wide range of shapes, and these are for sure the most exciting ones that feature complex topological and geometrical features. And in particular, I want you to focus on the second one here, that whose geometry features very large interior cavities that would be impossible to fabricate using state-of-the-art multi-piece rigid mold design methods, or even the silicon mold decomposition that I've shown you before in this deep dive, because these large interior cavities would make it impossible to extract a mold from it. Instead, our approach, being based on the composition of the object into multiple simpler parts, is able to create a successful rigid mold decomposition that only requires 3 parts for these objects. And this is another example of an object that features complex geometric details for which the generation of a valid rigid mold will be very hard. And again, our method, by decomposing it into 8 simpler parts, is able to produce a successful 2-piece rigid mold decomposition. Also here, I want you to focus on how the actual seams on the final object assembly are very barely visible just after some minor post-processing of the glued object. And this means that probably fine-tuning, like for industrial for industrial application, fine-tuning the tolerances on your mold fabrication step, the assembly seams will be really barely visible. So to summarize this deep dive, I presented you 2 methods based on object decomposition that solve different problems related in mold design. And as Marco was introducing in his motivational talk, these 2 methods are very different in terms of how we tackle the problem of designing a mold. In the first case, you've seen how a grid heuristic based only on geometric approximation of the problem allows us to very cleanly solve a very complex problem, that is soft mold, automatic soft mold design, that previous approach, for which previous approach would require a very complex numerical optimization-based methods. And I think that whenever it's possible, it's really important to focus on trying to find a good solution based on heuristics, because in a way it forces you to better look into your problem, and also it quite often leads you to having a very clean and efficient solution to very complex problems. And the second method instead that I presented you is based on a numerical optimization approach, and that allows you to express that problem in a very general way and also convenient way, because you can reduce it to a problem of multi-label assignment. But however, these kind of formulations have the problem of huge problems of scaling in terms of how big the problem can grow, in terms of the actual dimension of your domain. And so I think it's always preferable if you can come up with some greedy heuristic to look into it. And also I want to stress out the fact that both these methods are fully automatic, so they require no user expertise or no user intervention to output their results. And this can be seen as a good point, but also sometimes when you tackle problems related to design, this can also be seen in like a limitation. And in fact, quite often a designer or an engineer needs to enforce some functional or non-functional constraints over their design. And so they probably want to have a more finer control over the solutions output by their design method. So probably a very interesting research direction to look into in the next years would be to focus on figuring out how you can integrate these automatic methods in some interactive design process. And this is not an easy challenge, as current state-of-the-art methods, automatic methods, they often rely on very heavy computations that are far from being applicable at some interactive rate. And so I think that doing research in interactive mode design, like the one that was started by Nakashima et al. In 2018 with core cavity, could bring some new, interesting and challenging problems. And also another problem would be, interesting problem would be that of solving the design by manufacturability concept. That is a concept in which the designer is assisted during its design by some automatic oracle that helps the designer to enforce or guarantee some manufacturability constraints in its design shapes. So with this, I conclude my talk and want to thank you for your attention. And please, if you have any questions, don't hesitate to ask in the question time. Thank you.
Okay, very nice talk, Thomas. Actually, I have one question about this composite mode design.
Mm-hmm.
Okay, so in the composite mode design, right? So you intentionally create some cuts on the flexible mode, right? To take the object away, right? So
yeah,
actually, I'm just wondering the criteria to create these cuts, because for example, will this cuts affect the you will create artifacts on the fabricated objects? Do you want to minimize the number of these cuts? Maybe I missed something, but I just wondering this the answer to these questions.
Sorry, can you repeat the question? I have some loud noise in the office.
Okay. So in your composite mode, right? So you have this flexible part, and you create some cuts on the flexible parts, right?
Yeah.
For taking the object out from the mode.
Yeah.
I just wondering the criteria about creating these cuts. For example, do you want to minimize the number of cuts? Because I guess they may create some artifacts on the fabricated objects, right? Because there is a gap, right? The cut will every cut will correspond to a gap, and the material may go inside the gap.
Yeah, that's true. And so in the approach that we have taken in composite modes, being a fully greedy approach, we didn't work into minimizing the amount of these cuts that is introduced, but basically a cut is introduced whenever the check that I described you. Let me go to the slide. Okay, so So an additional cut is introduced whenever this case here, so this minimal approximation of a minimal surface intersects with the object. And experimentally, we have seen that quite often this leads to a minimal cut layout. And this really depends on how much noise you have on this check. And of course, each of these cuts, the additional membranes, will add some artifacts on your model, and the amount of how much this happens depends more on the fabrication stage in which you actually generate the MetaMods. Because if you are able to really fabricate very thin membranes in your geometry, then the gap will be very small, and also the silicon mold tends to stick together during the casting procedure, so that very few amount of resin would spill inside these gaps. So actually, when your cast comes out of your mold, it will have some membranes, depending on the casting material, that you need to remove and that you need to polish afterwards. But this is something that is usually required only also in industrial molds, where you quite often end up having some flashing, it's called, from the seams of the mold. So I think this is something that is tolerable in terms of a fabrication process.
Okay, yeah, that makes sense. Okay, so I have another question for Michael. So yeah, so in your motivational talk, you talk about 3 different methods to do the shape decomposition, right? So I mean, the mesh pulling, the graph cut, and this. Actually, I just wondering. So in case I want to have a curved shape cut, for example, when I want to fabricate something with stone, right? So sometimes I want the planar cut, but sometimes I might want a curved contact cut. That means the surface is like a very smooth. I mean, the cut is a very smooth surface. So if this is the case, so I want to know your comments or suggestion to do the shape decomposition.
Yeah, I think I mentioned that in the presentation. So the most typical thing that you find in the literature is planar cut, because it's simpler. It's easy to handle for many reasons. If you want to go with curved cuts, what you can do is to, for example, to operate with a volumetric discretization of your object. And you can define a continuous function, for example, an RBF, which essentially one level set of this implicit function will define your cut. This is something that, for example, I've personally used, not in the context of fabrication. I've used for volumetric hexahedral mesh generation. I had a paper 2 years ago at SIGGRAPH, I guess, that was called loopy cuts, in which essentially we designed a bunch of boundaries of cutting membranes that have to separate the volume, and the cuts were computed exactly in this way using Hermite RBFs. And so you get curved cuts. You can also play for manufacturing. This is something that I've never explored in a paper, but it's an idea that I had, and it's still in the shelf. When you define a cut in this way, so through a continuous function, typically you solve an optimization problem, something like least square something. And what you can do is to also have some sort of control on the gradient of your function per single element. And this is interesting because it allows you to sort of control the height fieldness of your cut. For example, if you want to assemble things together. It's not super easy. You may still have like vanishing gradients, so there is some kind of adjustment that you need to do, but it's something that you certainly can play with.
Okay, so I mean, so the method you mentioned about the based on the gradient or based on the high field, right? So okay, so I just wondering, so would you classify this as the bottom up or top down approach?
No, it's not. Well, no, this is something that you can associate very easily with top down, because with top down, essentially, you start with the whole domain, whatever representation you have is fine, and then you need to define your cuts. So it fits very well with that approach. If you go bottom up, for example, in the way that I've shown in the presentation, where you cluster elements of a discretization, it's different. Like the equivalent of curved cuts obtained through this approach is, for example, what Thomas and co-authors did for volume-aware molds, because essentially they are labeling a tetrahedral mesh. And so those cuts in the beginning will be facets, internal facets of the tetraherization. And then what they do is to essentially smooth this thing in order to appear smooth. So you can do in both ways, but this idea of implicit cuts applies only when you go top down, essentially.
Okay, yeah, that should be clear. Okay, yeah, due to the time limit, I think that should be the end of this session. So thank you both speakers for the excellent talk. Okay.
Thank you.
Yep.
Thank you for inviting.